Hello, welcome to the presentation of my research work. I am Ayan Banerjee. The topic is an investigation on the machinability of nitronic 50 using uncoated and coated carbide inserts. Background is the nitronic 50 alloy hails from the family of nitrogen strengthened austenitic stainless steel. It outclasses the family of AISI 300 stainless steels with better corrosion resistance and has almost twice the yield strength of AISI 316L. Thus, it finds its use in marine industry, bolting and shafting, petrochemical industry, nuclear fuel cycling, and food processing industries as well. Problem statement: from the extensive review of the past literatures, it has been found that there is a dearth of literature uh, pertaining to the machinability study of nitrogen strengthened austenitic steels, particularly nitronic 50. So it offered a perfect opportunity for researchers like us to explore the aspects related to the machinability of the alloy. Objectives: we carried out fundamental machinability study of nitronic 50 based on a host of responses using uncoated carbide inserts under dry environment. Similar study was being carried out using MTPVD and MTCVD inserts under dry condition, and we found a comparative analysis of between the two types of responses obtained between the two types of inserts. 3, 4, and 5 objectives are same. The only difference being the type of tool we used, and here we formed actually a comparative study between the different simulated responses, experimental responses, and predicted outcomes. And we also applied MCDM tools and meta-heuristic methods for optimization. Sixth is the cryo treatment of inserts we carried out, and following different schemes for 12 hours, 24 hours, and 36 hours, followed by tempering and double tempering, and we obtained several responses by machining the alloy using these inserts, and we formed a comparative study of the same. Then we carried out MQL based machining using uncoated inserts, and eighth objective is using MTPVD and MTCVD inserts. We studied several responses and formed a comparative analysis. So this is the graphical abstract and methodology. Result and discussion. This is the first objective. What we can see from the FZ plot: tangential cutting forces for a particular feed rate and depth of cut have increased with rising cutting speeds. Increase in cutting velocity has led to the increased friction, thereby raising the cutting temperature and BUE, which in turn had caused an upsurge in the requirement of cutting forces. The apparent coefficient plot maintained similar patterns. The tooltip temperature had maintained an increasing trend with increasing in cutting velocity and feeds. Highest tooltip temperature we can see at the intermediate level of cutting velocity due to low thermal conductivity of the alloy and increase in cutting velocity, which provided lesser time for heat dissipation. Objective 2, what we can see, CRC plots. Lower depths of flank wear are noticeable. In CRC plots we can see that under the combination of higher VC and higher depth of cut, higher CRC are obtained. The reason being rising friction, BUE, and tool wear. Lower depths of flank wear are noticeable for MTCVD inserts due to the fact that lower coefficient of friction with the top TICN layer in comparison to the TIN layer of PVD inserts, and better adherence of the TICN layer with the subsurface layer due to pin-shaped angular particulate nature of L2O3. Now objective 3, we can see percentage errors, computed average absolute errors for all the responses except for MRR have maintained below 5%, but this MRR that too for a particular trial has reached height. But from the ANOVA analysis, it is seen that R square value is 99.7% almost. So for the mentioned response, so the predicted model fitted well with the experimental data, we can say. Now objective 4, we conducted a 2-key test. Prior to that, one-way ANOVA was conducted to find out whether any significant differences existed among the different groups of experimental, simulated, and predicted datasets. Findings indicated that the p-values for all responses varied between 0.93 and 0.993, which suggested no significant differences between the groups. Objective 5, we can see this is a glimpse of the results obtained for the similar study conducted using MTCVD inserts, wherein flank wear had been estimated using Usui's empirical model. Objective 6, we can see grain size distribution, micro hardness, and thermal conductivity. So higher soaking periods for the 36-hour sample might have facilitated formation of dislocation entanglements, which might have acted as nucleation sites for grain boundary formation and hence finer grain size. Higher hardness was observed with the 36-hour soaked samples, reflecting optimal carbide precipitation and grain refinement. Similarly, thermal conductivity was high due to the redistribution of free cobalt, which has increased the tungsten carbide contiguity. Hence thermal conductivity was high for this particular sample. Now here we can see from the graphs, 36-hour soaked sample has led to favorable outcomes as well. Here the MQL study, we can see the SMD, solder mean diameter for soap water and propylene glycol were low, as well as the particle velocity were high. Here we can see from the graphs, both soap water and propylene glycol had led favorable results, but at higher speed soap water had suffered surfactant degradation and micelle formation, but due to glycol enhanced thermal stability, propylene glycol didn't. So that's why better responses were obtained between the two with propylene glycol water as a cutting fluid. So these are the major outcomes. You can see here are the major outcomes, references, these are publications. Thank you.